Chapter 4, types of reaction and solution stoichiometry. We just dipped our toes in the water on that chapter last Wednesday. Now we're going to finish up chapter 4. And I need to share the slides. There we go. And we need a slideshow. From current slide. There we go. So this is where we left off. Chemical reactions in solutions. Up to this point, we've been looking at solutions, chemical reactions in general terms, and how to balance equations, I'm pretty sure. Yeah. So you know how to balance equations, but the stoichiometry of reactions is just a little bit different for solutions because you have that solvent as a major component diluting your reactants. And in order for reactions to take place in solution, you generally start off with solutions and produce products that may or may not be soluble. So, enough of that for introduction. When we're discussing chemical reactions of solutions, we need to know something about the nature of the reaction. And by that I mean, for example, does the reaction produce an insoluble product? That's one type. It's called a precipitation. Does the reaction produce a gas, which should be readily observable in the solution itself? Does the reaction produce a change in color? You know, some of these macro indicators that a reaction is taking place. And then there are other things that you might observe that are characteristic of non-aqueous reactions also, like is there heat produced or does it absorb heat? Well, if it's in aqueous solution, the heat is not quite the issue that it might be in a non-aqueous reaction where you're reacting two solids or two pure liquids, because water is very good at absorbing large amounts of heat without making a significant change in temperature. It's sort of a heat buffer, they might say. Then we need a way to express how much of the reactants are in solution, because it doesn't just depend upon the total amount of reactants available. It depends more on the concentration of the solutes as to how they're going to interact, how they react with one another. Dilute solutions of the reactants will behave differently than concentrated solutions. Okay, so ways to express concentration. One of the most popular and most common that you'll see is called molarity. Molarity is, by definition, the number of moles of the solute that's dissolved in a liter of the solution. So if you got a liter, and this is 1 liter volume, and it's a 1 molar solution, you know that in that liter, you have 1 mole of solute. That's what it means. And it's very convenient expression of concentration, because once you've made the solution, there's really no good way to differentiate solute from solvent. So if you express the concentration in terms of the solute, the solvent volume, the solution volume, then all you have to do to know how much solute you have in your sampling is just to define how much volume of the solution you have. And it's like any equation, right? You've got 3 variables here. The expression of molarity, the number of moles, and the volume in liters. And if you know any 2 of those, you can solve for the 3rd one. So if we go one direction, say we know moles and we know volume, so we're going to solve for molarity. In this case, we have 6 moles of hydrogen chloride dissolved in 2 liters of solution, total solution. Then we calculate that the concentration of hydrogen chloride in solution is 3 molar. And of course, if that's an aqueous solution, then we name it differently. Now it's called hydrochloric acid. Okay, suppose, well, there's another problem. We don't have any instruments that will measure moles. We can't say, take, in this case, potassium phosphate, throw it on the balance, and tell me how many moles it is. It doesn't read out that way, because every compound and every element is a different molar mass. So, in the case of this 500-gram sample of potassium phosphate, we dissolve it in enough water to make 1.5 liters of solution. So what's the molarity there? Well, you need to know how many moles of potassium phosphate you have. When you've got 500 grams, how many moles does that represent? First of all, how do you convert 500 grams of a sample into moles? You need a conversion factor to cancel the grams and leave you with moles. Whenever you see grams and moles in a quotient like that, that's molar mass. So you need to know the molar mass of potassium phosphate. So how do you determine molar mass of potassium phosphate if all you have is the name? Well, that's why early on I was hammering, you've got to learn how to write these compounds. If you don't, it's going to come back to bite you. Potassium phosphate, you know you have potassium, right? And phosphate is not an element. Phosphate is a polyatomic ion. So you go to your little table. I don't think I have a copy with me right now. But you look up phosphate and you find out what's the formula, what's the charge. Right? And potassium, you know the charge of potassium because it's in the first group. The alkali metals are all +1. So in order to make the charges balanced, you need 3 potassiums. So there's your formula, K3PO4. Now you can determine the molar mass. All you have to do is look it up on your periodic table, add up 3 potassiums, right? So I'll look on my periodic table. 39.10, rounded off to 2 decimal places, times 3, because you have 3 of them, right? And then add that together with 1 phosphorus, which is 30.97. Just 1 of them. Now 4 oxygens. Oxygen is 16, rounded off to 2 decimal places, 16.00, times 4, which is 64. 212.27 grams. Per mole. So we divide that number into 500. We get 2.355. Now it's simple. You know the volume is 1.5 liters. And the moles of this. So I divide 1.5 into that, and I get 1.57 molar. That's the concentration of 500 grams dissolved in a final volume of 1.5 liters. Okay. Now suppose we know this one. We know that concentration. Now that we've made the solution, and say, I want to sample a certain volume of that solution that will give me 150 grams of potassium phosphate still in solution. You would convert 150 grams, like we did here, into moles, and then you would plug it in here, and you would have that one known and this one known, and the volume would be unknown. So you solve for the unknown. And then that tells you what volume of that solution you need to give you 150 grams. All right. Now, when we discuss concentration, very often solution stoichiometry involves soluble salts, that is, soluble compounds that break up into positive ions and negative ions. Calcium chloride here is our example. Sometimes you just need to know what's the concentration of the calcium chloride in the solution. Recognizing that when it goes into solution, it's not CaCl2 molecules anymore. It's not like that. It really is broken up into calcium ions and chloride ions. But for calculation purposes, maybe that's all you need to know. How much is calcium chloride? But if you need to know something about the ionic concentration, for instance, well, they don't do it anymore, but used to be, nurses and medical technicians were required to make up solutions for IVs, for intravenous injection into patients. And they had to know how to make up a solution that was isotonic with the patient's body tissues. If you didn't, and it was wildly different than the concentration required to meet that requirement, that's redundant. The concentration that was needed, then they could kill the patient. We've since done away with that. I mean, these solutions are pre-made, but somebody has to make them. Somebody has to know how to do this. And you have to take into account not the concentration of the calcium chloride molecule, but the concentration of the ions, because that determines what we call osmolarity. All right. So in this case, calcium chloride breaks up into 1 calcium and 2 chlorides. So the concentration of calcium ions is the same, 0.25 molar calcium, because for every 1 calcium chloride, it's going to be difficult. All right. For every 1 calcium chloride, when it goes into solution, it breaks up into 1 calcium and 2 chlorides. So if you know the concentration of this one, then it's 1 to 1. For every one of these, you got one of those. But for every one of these, you have 2 of those. So the concentration of chloride ions is actually double. All right. So what's the total ionic concentration in this solution? Okay. Sometimes that's important information. All right. So it's going to be difficult. All right. So for this problem, we want to know which one has the greatest number of ions, total numbers of ions. So if you have 400 milliliters of 0.1 molar sodium chloride, calculate the total number of ions. So you would have so many moles of sodium chloride and then times how many ions that is, times 2, would give you the total number of ions. Right? So we're still using this formula. And we want to find this one, first, the number of moles for the particular salt, and then times the number of ions per mole of the salt. So we would solve it for this, like that, and then we would do our calculation. Okay. Right? So if we have 400 milliliters, how many liters is that? There are 1,000 milliliters in a liter. So 400 would be 0.4 liters. 3 places to the left. times the molarity, which is 0.1. So that's 0.04 molar sodium chloride times 2 is 0.08. Not molar, moles. Of ions. And just do the same thing for each one. 0.3 liters times, oh, they're all 0.1 molar. All right. So 0.1 molar, and that's equal to 0.03 times calcium chloride is 3 ions per molecule. 0.09. This one, 0.2 liters times 0.1 equals 0.02 times iron 3 chloride makes 4 ions. 0.8. And then the last one, 0.8 liters times 0.1 molar. Okay, what's wrong with this picture? Sucrose does not ionize. So it doesn't matter. It doesn't make ions. So throw it out. Because the question says, how many ions? Which is the greatest number of ions? Well, our calculation so far says that this one, B, calcium chloride, under these conditions and these volumes, makes the most ions. Okay? So here we go again. This is problem solving 101. Where are we going? That's another way of saying, what's the question? If you don't know what the question is, you can't get the answer. How do we get there? Well, first you got to assess. If I know the question, right? So what information do I need to answer the question? You look at the problem. All right, it gives me this information, this, and this, but I need something else. Usually, you have to go to the periodic table. But sometimes you need to go to one of those tables or charts that I give you in useful information to find that extra bit of information you need to answer the question. And then go back and check yourself. You know, is this answer reasonable? Okay. So, I use a little elbow grease here. I don't know why this board's being so difficult today. Probably a mistake to clean it. Okay. When I was in research, we would have to analyze hundreds of samples by exactly the same technique every time. And very often that required making up a particular concentration of a solution, what we would call an extractant. For example, we would use a 0.1 molar, 0.1 molar hydrogen chloride aqueous solution, plus, if I can remember, let's see if I can remember this correctly, 0.05, I think, ammonium fluoride. So we would use that to extract phosphorus from the soil. And it's supposed to mimic the availability of phosphorus to plants. Well, that solution, you could make up enough of it to do your batch of samples, but it would take you maybe 30 minutes, 45 minutes to make it up, to make up enough solution. And it was a lot quicker if you would make up a concentrated solution that was 10 times that much concentration in a large batch, and then you would just have to dilute it to the concentration you wanted each time, and that would take 10 minutes. And I mean, if you made enough of it, it's fairly stable over a week or so, so you could make up a huge amount of diluted sample, and it would keep also for a while. But the concentrated sample would keep for months. Okay, so we need a way to know that we have the right concentration in the final solution based on the concentrated solution concentration and the dilution procedure. Okay. So that's what we're going to do now. And here's the way we do it. Perhaps I should show you how to make a solution first, right? What you need to know, if we're going to do molarity, what you need to know is the exact volume of the solution. You need some sort of container that's calibrated to hold a known volume, because you're going to put something into it and then you want to dilute it to that volume. That's the volume of the solution, not what you add to it, right? So what we do is we have volumetric glassware, and it's usually shaped like a long, narrow-necked flask. Something like that. And then there's a line drawn right here. And that line indicates that if you fill this up with a liquid, preferably aqueous, it's calibrated for aqueous, fill it up to that mark at a given temperature, you will have exactly the volume indicated on the flask. So let's keep it simple. Let's say it's 1 liter. One liter to that mark. Okay, so we want to make up a solution of, say, I don't know, ammonium acetate. That was a common extractant that we used to use. Let's see, C2H3O2. Okay, there's our ammonium acetate. Ammonium ion, acetate ion, 1 to 1. So we take a certain amount of that, whatever is required, and we should actually put some, we have a little bit of water in the bottom. So we put that in here, it accumulates on the bottom, and you mix it to dissolve it. Won't quite dissolve, add a little bit more water. But you want to keep it below that level, because many of the salts, in this case, that you add to water and dissolve are either exothermic or endothermic. Very few of them have a stable temperature in the process. In fact, ammonium acetate, I think, is endothermic. It'll get cold. So once it's dissolved, you can add a little bit more water, up to about here will be okay. And then mix it. Make sure it's completely dissolved and let it sit until it dissipates the heat or absorbs the heat that's required to come back to room temperature. Because these flasks are calibrated for roughly room temperature. Actually, they're marked on the flask, the calibration temperature. But if you're very close to what we consider normal room temperature, then the difference in volume is not that much. So it won't affect your results. Anyway, once it's dissolved, then you can add water up to the mark. And so the aqueous solutions have a concave meniscus, right? So it's going to be like this. When it's at that mark, then you cap it and shake it. Mix it up really good. Now you have exactly the concentration that's your target. Now, if that happens to be very concentrated, so you have to dilute it later, then you know what it is right now. Okay, so that's how we would make a solution. If you make that solution and it's endothermic, it gets cold, that means the volume shrinks. So if you bring it to volume when it's cold, then as it heats up, it's going to expand and it'll be above the mark. And you got to start all over again. Of course, if it's exothermic and it's hot, and you bring it above the mark, not too far, then it'll cool down and shrink, and then you can bring it back up. But it's better to wait for it to come to room temperature before you do the final dilution. All right. So now we have a concentration of a solution that's M1. Okay. And we want to produce a solution that's a different concentration, M2. Okay. So this is the more concentrated and that's the more dilute. Maybe I better change the subscripts. This is concentrated and this is dilute. How about that? So now, what would this expression look like if we broke it down? It would be the number of moles per a unit volume, right? So the volume of the concentrated gives us so much moles of the concentrated. And if you rearrange this, like that, right? So that's valid. Moles of the concentrated times the volume. And this volume I'm talking about for the concentrated, it's the volume that you extract from the solution, an exact known amount. At that concentration gives you this many moles. Now, we're going to put this many moles into a new vessel and dilute it to a new volume. Right? So we take this volume of that concentration and we put it into a container that has a known volume, and that volume is over here. So we can rewrite this one the same way. Let's do it this way. Like that. So it's a similar equation, only I just flipped it to put the moles on the inside. This is the new molarity that we want, the diluted molarity. And this is the volume of that new molarity right here that we're going to dilute it to, that volume. So we're going to take this many moles, put it in here, dilute it to that volume so that we can get this concentration. Well, what do these two equations have in common? Right there. The moles of the concentrated and the moles of the diluted are exactly equal. Right? When we pull this out of the concentrated, we have that many moles. When we put them in here, does that change? No, it's got the same number of molecules as it did before. So these two are equal. Now, since they're equal, just get rid of them. Now this is equal to that. Or M1V1 equals M2V2, both ways. That's where that formula comes from. And it's all based upon the fact that moles equals moles, before and after. Okay, well, I've got a slide that does that right here. So that's what it's saying. Now that we know that that's true, we know that this formula is valid. Okay. I'm going to skip this one. I'll let you read it. But I want to be sure that we don't run out of time. In fact, I'm taking longer than I expected. I've only got 20 minutes left. So what's the minimum volume of a 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? So we're going from a concentrated to a diluted. So since this is a word problem, it's helpful to extract that information and put it on the board with its proper designation for each of the values. So we're looking for the minimum volume of the 2 molar sodium hydroxide. So the concentrated volume equals 2 molar, and we need to pull out, the concentrated molarity. The volume that we need is unknown. That's the question. Where do we want to end up? Well, we want a molarity of diluted solution equal to 0.8. And the final volume of the diluted solution, 150 milliliters. Okay, so there's all the information. And if you do it that way, then you won't get your volumes switched. Because if you switch them and put them in the wrong place, you'll get the wrong answer. Now, one other point I'll make. With this expression, notice that we can rearrange that and show ratios, right? Volume and volume. If we rearrange, we get this right over here, and this one over there. Notice that if the volume of the concentrated is in milliliters, and these are molarity, right? Then what's your answer going to be in? Your answer is going to be milliliters also. So with this type of ratio, you don't have to change to liters to make it work. It's only when you're using the standalone formula, molarity equals moles divided by volume, that you have to change to liters. But when you've got a ratio like this, you can leave it milliliters and save yourself a step. So we can leave this milliliters and plug the numbers in, or you can solve it for your unknown, right? Solve it for this one. So now we've got molarity here, 0.8, volume, and molarity here, and just solve it for that. Let's see, is that 2? That's 150. Okay. So 2 into that's 75, and 0.8 times 75 is what? It's easier to do it this way. 2 into 8 is 0.4, and 150 times 0.4 is 60. So what does that mean? That means that you take 60 milliliters of the concentrated solution and dilute it to 150 milliliters final volume, and that will guarantee you have 0.8 molar sodium hydroxide. Let's see if I'm right. Yeah, okay. There we go. Oops, I'm sliding off there. Okay. Let me check my roster to see if anybody else showed up. I suspect, because there are 8 students, and I've only got 3 marked off. So let me get everybody covered. There we go. And no, not here. Let's see. I need to expand this a little. Yeah, I need to expand that some. There we go. Okay, not here. 1, 2, 3, 4, 5, 6, 7, 8. Who am I missing? Got it. Okay. Back to chemistry. That just emphasizes the point. In this type of formula, where you have a ratio of concentrations that will cancel one another out, you don't have to change the volume. Now, there's one measurement where that never works, and that's temperature. When we do calculations using temperature, unless the formula specifically requires Celsius or Fahrenheit or whatever, then just assume you have to convert the Celsius to Kelvin. All right, types of reactions. Reactions are classified based on what they do. And many of the classifications overlap. In other words, you can have a reaction that's multiple types. Major types, precipitation reaction, right? Those reactions in which a solid is produced as a product. And you will know when you have a solid produced because it'll get cloudy. Another way to tell is called the Tyndall Effect. I think it's got two L's. Tyndall Effect. Okay? If you have a solution in a beaker, like that, and that solution, you shine a light through it. Shine a light through it, and you can see from this side, you can see the light beam coming out that side, right? Even if it's not a solution, if it's got a precipitate in it, suspended, you know, floating around. Very fine particles, even. If it's a solution, you won't see the light beam from this right angle. Right? You won't be able to see the light beam. If it has a precipitate forming in it, even if it's the most microscopic particles, but now it's a suspension, then you will be able to see the light beam because the particles scatter the light, whereas in a solution, they don't. Okay, that's the Tyndall Effect. And that's one way that we determine that a precipitate has formed. Sometimes it's obvious, right? The precipitate might be a different color, right? Chromate precipitates are usually yellow, so they're easy to see. It's a little more difficult if you have a silver precipitate, a silver chloride dropping out of solution. It's very difficult to see that as a precipitate because it's so finely divided. But the Tyndall Effect will expose it at very, very low levels. Okay, acid-base reactions. So that's just what they are. You add an acid to a base, you get a reaction. Every time, as a matter of fact. Or it could be an oxidation-reduction reaction. Now, I'm using a term there that we haven't defined. But oxidation-reduction reactions require transfer of electrons from one reactant to the other. Okay, that's enough for now. Other types: combination reaction, a synthesis, where you have two simples making something more complex. Combination or synthesis reaction. Decomposition is just the other way around. It goes back this way. This is a reactant, and it makes simpler. And usually when it does that, it makes elements. Decomposition. Single replacement is where you have an element and a compound, and the element replaces one of the components in the compound. So let's say this is a metal, and it replaces that metal here. Oops, yeah, let's see. That's a single replacement or a displacement. Now, if you have something like this, AB plus CD, and these two swap, so you have a CB plus AD. That's a double replacement. And these are the types of reactions that typically, well, they don't always, but they can produce precipitates. These two will be soluble, water soluble, usually, in our case. And then when you recombine them, one of them is probably still soluble and the other one's not, right? So these would be aqueous. Maybe this one might be aqueous, but this one will be a solid. It precipitates. Another type of reaction, combustion. A combustion reaction requires oxygen. It has to have oxygen. And then it has to have something that will react with oxygen. Your Bunsen burners, for instance, they'll have methane. So that's a gas, this is a gas. And they'll produce carbon dioxide and water. Now that's not balanced, but those are the products. That's a combustion reaction. It's also an oxidation reduction reaction. And I'll have to prove it to you first. But I'll just throw that out there and then we'll come to that in a minute. Okay. Precipitation reaction is also a double replacement, like I mentioned earlier. If it forms a precipitate, it resulted from a double replacement. This is an example. Right? If you combine, let's see, barium nitrate. Let's see, barium is the purple, potassium is the red, nitrate is this 4-atom combination, and chromate is this 5-atom polyatomic ion. Now what happens? Well, the barium combines with the chromate and becomes insoluble. So that's why it's down here on the bottom of the beaker. And this is a photograph of what really happens. I mean, this is a true picture, right? The potassium nitrate here is still in solution, and it should have an aqueous out here to the side. So that's an example of a double replacement precipitation reaction. This is not going to work for the same reason as all of my flash. Since flash is no longer supported, it doesn't work anymore. So I got to get rid of that slide and replace it with something else. Okay. Precipitates. All right, we can classify precipitates based on, well, not classify precipitates. We can classify compounds as either soluble or insoluble. And we're still talking about aqueous solutions. But the fact of the matter is that some compounds are just so slightly soluble. For now, we're going to draw a distinction between soluble and insoluble. And we're going to leave the discussion of slightly soluble to later when we talk about actually determining, quantifying the solubility. Right? For now, it's a generality. I just want you to recognize that nearly all compounds have some solubility. I mean, it may just be as slight as 10 to the minus 20th molar in solution. I mean, that's virtually insoluble, but I mean, it's measurable. So we'll leave that till a later discussion. Now, these are the rules that I'm not going to require that you memorize these rules. I just put them there to show you that any compound with nitrate in it is soluble. And these are organized 1 through 6, I think. Yeah, 1 through 6 in such a way that if you have a conflict between two of the rules, like both of the rules apply to the situation, the one above takes precedence. Okay, we can say that most of the alkali metals in the group 1 are soluble, and ammonium compounds are soluble. Most chloride, bromide, and iodide salts are soluble, except for these right here: silver, lead, and mercury 1. Notice that that's mercury 2 times with a 2 plus charge, which means each mercury is only +1. Right? So that's why I said mercury 1. But those are insoluble. Most sulfate salts are soluble, except barium, lead, mercury. Actually, this is mercury 2 right here. Why? Because I know sulfate is a 2- charge, and you need a 2+ charge. No, this is mercury 1, excuse me. This is mercury 1. Mercury 1+ times 2 gives you a 2+. So a 2+ and a 2- neutralizes. But they're insoluble. Calcium sulfate is insoluble in water. Where do we know calcium sulfate? Well, in the laboratory, it's called dryerite. It absorbs water from the atmosphere, and we use it in desiccators to keep the atmosphere inside the desiccator completely dry. So if you heated something up and you want it to cool down without absorbing water, you put it in a desiccator. But calcium sulfate, you'll also find in your walls. Calcium sulfate is present in gypsum. Okay? Only gypsum is like this. It has 2 waters of hydration, right? And when you do that lab, pretty sure you have that lab to do, waters of hydration and waters of constitution, that lab talks about compounds that have waters of hydration. I think the one we're using is copper sulfate. Okay, most hydroxyls are only slightly soluble, so they're basically insoluble. Sodium hydroxide, potassium hydroxide are definitely soluble, completely soluble, whereas barium hydroxide and calcium hydroxide are only slightly soluble, and we would consider them insoluble for our purposes now. And then last but not least, sulfides, carbonates, chromates, phosphates are only slightly soluble, which means, for our purposes, insoluble, except for those that are combined with cations in Rule 2. Right? If they're combined with alkali metals or ammonium, then they're soluble. Otherwise, they're insoluble. Okay, now all of those rules aside, there's a chart. Where is it? There it is. I had to skip a few slides. So on this chart, you got the cations, or the positive ions, across the top, and then down the left-hand side, the anions. So all you have to do is just read it like a mileage map, a mileage chart on a road map. I don't know if they do that anymore. People don't use maps. They use Garmin and apps to do that. But it used to be, if you wanted to find out how far it was from one place to another, you looked at the map and you found the 2 locations, and then you looked at a chart and you followed one location on the top and then the other location on the side, and you followed down until they met in the middle. And there was a mileage, a number there. Well, it's similar here. You find your cation, you find your anion, you follow them to one side or up and down until they meet. And then you look at the square. Is it clear, which means they're soluble, or is it grayed, which means they're insoluble? Okay, and then you got all the rules down here at the bottom, just as a reminder. If you use this chart enough, then some of these things are going to start to sink in, and you'll just know them. But if you don't use it at all, then I feel sorry for you, because it's not going to be a pleasant experience. You need to practice using that chart. That's what those review questions are all about. Okay, so let's go back and let's see, 3 o'clock? Oh, I don't know what I was thinking. I got another 45 minutes, don't I? Okay, which of the following ions form compounds with lead 2+ that are generally soluble in water? So you get your chart out and you look at each one of these compared to lead, right? There's your cation, and you follow the anions until they meet, and you find out, is it soluble or not? Well, which are generally soluble? Well, the sulfides are not soluble. The chlorides, no, lead chloride is not soluble. Nitrate is soluble, right? Sulfate is not soluble. So these three right here are not soluble, and that one is soluble. And this one is thrown in there just to see if you're paying attention, right? A cation and a cation don't combine to form a compound. It just doesn't work that way. You have to have opposite charges. Okay. Now, when we write these equations, these double replacement reaction equations, if there is a reaction that produces an insoluble compound, then that, in fact, is the driving force for the reaction, because the insoluble compound drops out of solution, and as it's being removed from the solution, it can't play anymore. So removing that from solution like that as a solid drives the reaction toward this side, the product side. Okay, so we need to be able to balance the equation, and we already know how to do that, right? We balance the equation, and then we break the equation apart into reality. The reality is, if this compound is soluble, then it does not exist in solution like that, molecular. That's why we call this a molecular equation. It's actually a convenience. It's a lie, because this compound exists in solution as the ions, silver ions +1, nitrate ions -1 in solution. So if we break it apart, after we balance it, then this is what we actually have. Silver ions, nitrate ions, sodium ions, chloride ions. They're all just mixing it up, solutes in the solution until they meet. And when the silver meets the chloride, they form a very strong bond. It will not allow the ions to re-enter solution as ions. So that silver chloride drops out of solution. Now these guys, sodium and nitrate, they're still happy to go along. Sodium nitrate is soluble. Just look it up in the chart. So those ions stay put. They're still in solution before and after. Now, what do we know about equations that have equal species and numbers on both sides of the equation? If you want to, you can cancel them, right? If it's here on the going inside and here on the coming outside, just cross a line through them. And what you get is the net ionic equation. Let's look at that again. This one combines with that one. This one combines with that one to make that one. But these two don't combine. This is the complete ionic equation. The net ionic equation cancels out those spectator ions, we call them. The spectators are gone in the net ionic equation. Now, what's the value of doing that? Well, here's one practical example. Suppose you want to carry out this reaction right here, and you know that the spectators in that reaction are sodium and nitrate. Well, look what you can do. Suppose you have a nitrate compound on your shelf. Let's see, is that right? No, suppose you have a chloride compound on your shelf other than sodium chloride, say potassium chloride. Right? You can substitute potassium for that ion. It's just a spectator, right? As long as the potassium is on both sides. Potassium nitrate is soluble, so it would work just as well for this reaction as sodium chloride. Sometimes you have to do that, especially if you're teaching at a community college and your budget is practically nothing, then you can't afford to buy just anything you want when you want it. So I might have to use potassium chloride instead of sodium chloride for a demonstration or for a lab experiment. And it would work perfectly well because this is the reaction that we're interested in right here. As long as you can get that chloride in solution, along with that silver in solution, you'll get that exact same reaction. All right, so here's an example. You've got a couple of examples also in your review document for writing the, well, this is called the formula equation, the molecular equation, which actually a formula equation is a better term for it. But we don't have time to discuss that right now. Formula, molecular equation, they're synonymous. So what you have is what we are calling complete formula units here, and they're giving us formula units here and here. Only this one's solid, and the other one is still aqueous. So you break them apart into their ions, right? You can't do the solid that way. Solid has to stay put. And then you cross out the spectator ions, which are ions on both sides. Sodium's on both sides, and chloride's on both. No, not chloride. Sodium's on both sides. Wait a minute. That's wrong. Sorry, that's a mistake. Notice the chloride is a spectator. That should be hydroxide. So instead of OH, I put chloride. It should be two OHs. So let me make that correction here and I'll fix it. There we go. All right. So pay no attention to that man behind the curtain. It should be a hydroxyl. OH minus right here. Because we cancel the chlorides and we cancel the sodiums. They're on both sides of the equation. They're spectators. Okay. Now, once we've got a balanced equation, how do you do the stoichiometry with a balanced equation? Well, let's see if we got an example. That might work better. These are the rules, right? The steps. But, okay, this is a good one. Looks like it's coming in parts. So if we do it once, then the next part we'll probably use the same balanced equation. So we'll balance our equation first. What do we have? 10 milliliters of 0.3 molar sodium phosphate solution reacting with 20 milliliters of 0.2 molar lead 2 nitrate solution. Okay? And notice that all nitrates are soluble. Right? So this lead nitrate is soluble. It's in solution. And you just pour the, let's see, over here. Pour the 2 solutions together. 10 milliliters of one, 20 of the other. And what do you get? Well, we have to know first the compounds. So we have sodium phosphate. We know that we have this one and this one. Right. So this is a 3 minus. This is a 1 plus. We need 3 of those. And this is aqueous solution. Okay? You can erase the charges if you want, but I just put them up there for bookkeeping purposes. And we're going to add to that lead 2 nitrate. Lead, it has a 2 plus charge, and nitrate has a 1 minus charge, which means we need 2 nitrates. That's a polyatomic ion. You can't break it up. Like that. Okay? Now I'm going to wrap around. So, how do you do these double replacement reactions? We know that they form independent ions in solution. So we just swap. Replace this one over here with that one and bring that one over here. So what do you get? You get lead phosphate. 3 minus, 2 plus. Now how do you balance that one? Right? Odds and evens, cross multiply. Bring the 3 over here. And the 2 over here. Right. Now we have sodium and nitrate. One plus, 1 minus, that's balanced. And it's soluble. But if we look at that chart, lead 2 plus and phosphate, let's go back. Here we go. So lead 2 plus, where is lead 2 plus? I got to move this thing out of my way or I can't see. Lead 2 plus right here. Okay. Then we follow down until we reach phosphate right here. See, there's phosphate over here. It meets lead right here. It's gray, insoluble. There's your solid. Okay. Now we need to balance the equation. If you're going to do stoichiometry, you have to balance. You don't have any choice. Okay? Well, let's answer this first question. What precipitate will form? Well, there it is. Lead phosphate. Lead 2 phosphate. Pb3, PO4 taken twice. Okay, that answers the first question. What's the balanced molecular equation? All right. So this uses that one trick that I told you about. When you have polyatomic ions that are present as reactants and products, and they don't break apart in the process, they don't splinter and show up different places, then you can use those as balancing units, right? Phosphate here, phosphate there. Sodium, sodium, lead, lead, nitrate, nitrate. Okay? So you can use your budget. I can't use the budget here because I wrapped around, so I can't draw it right. So I'm going to do it in my head. But if you string it out on a piece of paper, then you can use the budget. You can say sodium, phosphate, lead, nitrate, and then use your budgeting. But I need 3 of these sodiums, 3 sodiums. That gives me 3 nitrates. That gives me, 3 nitrates. Let's do the leads first. 3 leads. Okay. So that gives me 3 leads, 6 nitrates, okay, 6 sodiums, 2 phosphates, 2 phosphates. Now we're balanced. 2, 3, 1, 6. Okay. Now that our equation is balanced, right there, then we can use it to do stoichiometry. Let's go back. What mass of precipitate will form? Okay, so we want to know the mass of this compound right here. I should have spread it out more, actually. Let me see how I'm doing on, where am I located? Okay. All right, we'll do part of it anyway. What mass of precipitate will form? Okay, I'm going to have to rewrite this so I can do the stoichiometry. So let me do this 2 sodium phosphate and then plus 3 lead 2 nitrate, right? Yields lead 2 phosphate plus 6 sodium nitrate. There we go. Now we can do stoichiometry. Okay. All right, now what are we given? We've got the balanced equation. We're starting off with 10 milliliters of 0.3 molar sodium phosphate. 10 milliliters of 0.30. Actually, that's got 3 significant figures. Okay. There we go. And we're going to combine it with 20 milliliters of 0.2 molar. Okay. So what do we know? We know 2 things. We know that we can't get here until we have moles. We got to have moles. We can't get there with milliliters. We can't get there with molarity. We couldn't get there with mass. The last time we looked at stoichiometry, right, last chapter. It's got to be moles. So how many moles do we have here? Molarity times volume equals moles. So we just need to change this to liters multiplied times molarity. That gives us moles. So milliliters, right, is how many liters? Times 10 to the minus third, right? 1,000 milliliters, 1,000. So we're going to convert this into 10 to the minus 3 liters, and this times 10 to the minus 3 liters. Now when we multiply them together, we get moles. So let's see. Make it easy on myself. That times this is 3.0 times 10 to the minus 3 moles. Okay, and this one is, I bet it's 4 times 10 to the minus 3 moles. Okay, now we can go somewhere. Except when you have two reactants in which the problem gives you exact amounts of each one, what should that mean to you? That means one of them is limiting. One of them's going to run out, right? And that's the case. So how do we determine which one's limiting? We take this one and convert it all the way over to this one. And we take this one and convert it all the way over to this one. Compare the two. And the one that makes the least amount is the limiting reactant. And in fact, the one that makes the least amount is the number of moles for this one. And once we find that, we can convert it back into mass using molar mass of that compound. Okay, so let's go ahead and do that. If we got this many moles of lead nitrate, how many moles of that do we have? What's the ratio? Well, we got 3 of these that we want to cancel. And we got 1 of those. So 1/3 of that, which should be 1.33 times 10 to the minus 3 moles of that compound. This one what's the ratio there? Well, this has 2 to 1. So we just take half of that one, 1.5 times 10 to the minus 3 moles. All right, now which one's limiting? That one right there. So we'll take that one here, and we'll use this one. So now we know how many moles of that we have. Convert it to mass. Right? Molar mass. So what's the molar mass of Pb3PO4? This needs to be a 2. Yeah, okay, just checking. Okay, so we need the molar mass of lead, lead 2 phosphate. Okay, we just need to add up 3 leads. So I need to look it up. 207.2. 207.2 times 3. And 2 phosphorus, right? 2 times that, 2 phosphorus, which is 30.97 times 2, then add that together. And then how many oxygens? 8. So 16 times 8. Add that in. So it's, is it that much? I better check my numbers. Lead 207.2. Yeah, I'll do it again. Okay, I think I got it right the first time. I'm just checking myself. 30.97. And then 8 times 16. That's better. I must have hit the wrong button earlier. This is 811.54. Times 1.33 10 to the minus 3. So that's 1.8 grams. Zero 8. 1.08. Okay. Now let's see if I got even close. Okay, there's limiting. Yeah, the value of moles. Okay, I'll have to explain this in just a second. Let me see if my answer came out right. Yeah, okay. You'll notice that I'm using a different measure of moles, millimoles. Okay. It's not as cryptic as it might look. When you multiply molarity times liters, you get moles. That's the definition. But if you multiply molarity times milliliters, you get millimoles. And if you divide millimoles by milliliters, you get molarity. So that's just a way of skipping steps. As long as you keep track and know what you're doing. When I say I'm converting these to millimoles over here, over here, and over here, well, when you get ready to do the conversions to mass, you're going to have to go back to moles. So when I go from here, 1.33 millimoles of lead 2 phosphate to moles, I just tack on a 10 to the minus third, because that's what milli means, 10 to the minus third. Okay, so let's see, did I miss anything? No, we're good. Got the answer there. This question is asking, when you do this analysis, what's the concentration of nitrate ions left in solution after the reaction is complete? Okay. I need to keep this here. Let's see. I don't need this one. Erase that one. I'm going to leave that part there, because that belongs to this one. Okay. What do we know about nitrate here? Nitrate's on both sides of the reaction. And in each case, it's soluble. So the nitrate ions you start with are the same nitrates you end with. Right? Nothing has happened to them except they stay in solution. So the only thing that's happened to the nitrates is now they're in more volume than they were before. Right? They started out in 20 milliliters of volume, and now they're in 30 milliliters of volume. So we just need to find out how many there are and divide by the total volume. All right? So how many moles of nitrate do you have here? Well, There's the moles, but it's 2 for every 1. So you actually have 8.0 times 10 to the minus third moles of nitrate. How many liters do you have? Well, 30 milliliters is 0.03 liters. Right? So we just do a little math. You get 0.27. That's in your final solution. Okay? This one's a little more difficult. What's the concentration of phosphate ions left in solution after the reaction is complete? Well, notice that phosphate started out here with this many moles, but now it's over here. Some of them are in the precipitate, right? Did we use all of them up, though? No. We didn't use up all the phosphates because they were excess. Remember, these were limiting. These were excess, right? This was the lesser amount, so it yielded that. And this is the greater amount. Okay? So we used up a lot of the phosphates, but not all of them. So how do we tell what's left over? Well, how much did we use up? If we have this many moles of that solution, right, of that total solution, how many moles of phosphate is that? Well, it's 2 moles of phosphate for every mole of compound. So we actually used up 2.66 times 10 to the minus third moles of phosphate. Okay? How much did we start out with? Well, there's 1 for every 1. So we actually started with this amount. So how much did we have left over? Well, subtract that from this. Okay? Since these powers are the same, we can just subtract these 2. Okay? So that's how many moles. That's not scientific, but that's okay. We can plug it in our calculator just like that. In a final volume of what? 30 milliliters, or 0.03 liters. So we divide this by 0.03 liters. And I get 1.13 times 10 to the minus 2. 1.13 times 10 to the minus 2 molar phosphate aqueous. That's what's left in solution. All right, we rounded it off here. So this is 1.1. I said 1.13. Okay? Now, we're going to switch gears to a different type of reaction. So let me get rid of all this stuff so I have room to talk. I can't talk with an empty hand. Oh, maybe I've got some Italian in my background. But I don't know if anybody here is Italian descent, but I've always heard that the joke, how do you stop an Italian from talking? He ties his hands behind his back. Okay. Acid-base reactions. Now this is in terms of Lowry-Bronsted, and you don't know that yet, but you will. And all it says is that the acid donates a proton and the base accepts a proton. And a proton is a positively charged hydrogen atom. And based upon the majority of the isotopes of hydrogen are one proton, one electron, then if you strip an electron off, you just have a proton. So here's your proton, or your hydrogen ion, in solution, and you add a base, in this case, a hydroxyl. This one, the acid was the proton donor, excuse me. This equation is the net ionic equation. So let's start with something real. Like if we had an acid like this one, plus a base, what do you get? Well, double replacement, right? Sodium goes with chlorine, which is soluble. And then water. As it turns out, this reaction prefers to go that way because water does not dissociate well back to this direction. It wants to go that way mostly. So what do you have for your net ionic equation? You have protons plus chlorides plus sodiums plus hydroxyls, yields, sodiums plus chlorides plus water. Okay? So there's your molecular equation, your complete ionic equation. And notice you've got chloride on both sides, you've got sodium on both sides, and your net ionic equation is this. Okay? That's what that is right there, the net ionic equation for an acid-base reaction. All right, there's another failed video. Okay, the procedure for doing an acid-base reaction is almost identical to a double replacement. Right. So what that means is this is your net ionic equation for an acid-base reaction. So all you need to know is protons, you know, how many moles of proton are going to the reaction, how many hydroxyls go into the reaction, produces so much water. So very often we refer to as acid-base reactions in terms of how they are performed. And acid-base reactions typically are performed in a stepwise manner. You have a known amount of one. Let's just, for argument's sake, let's say you have a known amount of acid in a beaker. Just for example, hydrochloric acid. And then you have a device called a burette. And it's marked, it's calibrated in milliliters and tenths of milliliters. Okay? So that allows you to put your base in here and add it in small amounts until you know that you exactly have equal hydrogen ions and hydroxyl ions. So this is a stoichiometry where we call a titration. Now there are a whole host of different titrations. This is an acid-base titration. This sodium hydroxide is a known concentration. You know exactly what its molarity is. So when you add so many milliliters of it, you know how many moles of base have been added. And this many moles of base, when you reach exactly equal amounts, you know how much acid is in this container. Okay? And if you know how much volume you put in there in the first place, then you can calculate what the concentration is of that acid. That, in a nutshell, is an acid-base titration. The thing about it is, you can tell the point of equivalence when you have equal amounts of this and this if you are watching the change in acidity, the pH of the solution. I know we haven't defined that yet, but once you know that these two are equal, that's called the equivalence point. But in order to do that, you have to use a pH meter, and you have to watch the curve, and at a particular point on that curve, you know that's exactly the equivalence point. But if you have 100 of these things to do in just a couple of hours, that's not the best way to do it. It's not the quickest way. So you substitute something in your solution that will change color when it gets close to, if not exactly on, the equivalence point. And when it changes color, we call that the end point. It's an approximation of the equivalence point, and it's really pretty close. So the laboratories that we would do in our class, where we need to see the endpoint, we generally use phenolphthalein. And it'll change from clear, no color, if the solution is acidic, and it'll go pink when it reaches the endpoint. All right. Oh, okay, I'm out of time. Yep, I'm out of time. But I'm going to keep talking. If you have to go, then that's fine. Let me just be sure. Yeah, 9 people. I think I've got everybody who showed up is credited with attending. And I'm just going to finish this out. We just got a few more slides, but I want to get it done in one fell swoop. Then when we come back on Wednesday, we can start a review on Chapter 3. You can spend all the time we want on Chapter 3 because we have that following Monday to do Chapter 4 review. Okay. So for this titration, sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the end point? Okay, and the end point is an approximation of the equivalence point. The equivalence point is just what it says. The equivalence point is when the number of protons is equal to the number of hydroxyls. So it's really a stoichiometry problem. So we need to know the reaction, the chemical reaction for sodium hydroxide and sulfuric acid. There you go. Now we just need to balance it. Right. So we need 2 sodiums, makes 2 hydroxyls, and we need 2 waters. There we go. Now, that one's balanced. Now what we can do is say, what does the problem give us? We want to react sodium hydroxide with 1 liter of 0.5 molar sulfuric acid. So we got 1 liter of 0.5 molar, right? Volume times molarity equals moles. So this would be 0.5 is, 0.5 moles, and this is of sulfuric acid. Okay? So, if we convert this into that to find out how many moles we need here, which is the question, how many moles of sodium hydroxide, then our conversion factor would say H2SO4 to cancel these 2, right? And this would be the moles of sodium hydroxide required. So what's the ratio? Well, 2 to 1. So we need 1 mole of sodium hydroxide. Notice that it takes 2 moles of sodium hydroxide for every 1 of sulfuric acid. The reason for that is 2 hydrogens have to be neutralized. So it takes twice as much sodium hydroxide, which only has 1 hydroxyl. All right. Now let's switch gears to a different type of reaction. The redox reaction. That stands for oxidation reduction. Okay. Like I said before, this type of reaction occurs whenever electrons are transferred. So we'll look at an example in a minute. What I'm saying here is just a reminder, if you have a combustion reaction, it's always oxidation reduction. And I'll show you why in just a minute. Also, reactions which have an element on one side and that same element is in a compound on the other side of the arrow, those are also oxidation reduction reactions. These are examples. Right? When you combine sodium metal with chlorine gas, you get a violent reaction and table salt. Okay, so for this reaction, what has happened? Well, sodium is a solid, chlorine is a gas, makes sodium chloride, solid. So this is an ionic compound, right? So we know that sodium is a +1 ion because it comes from the alkali metals, and chlorine is a halogen, so it's a -1. But what's the charge on these guys over here? 0. 0. No charge. So what has happened? Well, for this one, we gain 1 electron. And for this one, we lost 1 electron. Okay? That's a redox reaction. Based on the economy of the electrons, plus on our rules, our hints, we have a metal here, an element here, it's in a compound over there. We have an element here, it's in a compound over there. Those are always redox reactions. Now, why do we call them redox? Well, this process, the loss of an electron, is oxidation. That process is oxidation. This process is reduction. Okay? How do you remember that? Oxidation is loss. Reduction is gain. Oil rig. Anytime you have a loss of an electron by any species, it has been oxidized. Anytime a species gains an electron, it has been reduced. And they always occur together. You can't have one without the other. Whenever there's an oxidation, there has to be a reduction. Okay. Now, how do we keep track of this movement of electrons? We do it by a process called oxidation states. And we need some rules, right? Okay, first rule, the oxidation state of an atom in an element is 0. So if you have the pure metal, oxidation state 0. If you have a diatomic, say hydrogen, that's the element, each hydrogen is 0. If you have this phosphorus, each one is 0. Or if you have this sulfur, each one is 0. They're all 0 oxidation state, which implies neutrality. Rule number 2. Any atom that becomes an ion, the oxidation state of that ion is the charge. So the oxidation state for sodium as an ion would be +1. The oxidation state of sulfur in a compound is -2. Okay? There's one exception. Oxygen, when it's combined with itself in a compound, is only -1, such as hydrogen peroxide. Now, both of these together would be a 2- or a -2. Each one is a -1. Okay? Hydrogen. Hydrogen in most situations and in all covalent compounds, hydrogen is a +1. It's like a proton. The only time hydrogen takes on a negative oxidation state is when it's combined with a metal, like calcium hydride or sodium hydride. Right? Then it becomes a negative one. Fluorine is a -1 in all compounds. That's the only possibility for fluorine. Now, the other halogens, like chlorine, bromine, iodine, those can be multiple oxidation states. You have to calculate those. But if there's a fluorine there, it's a -1. Rule number 6. When you add up all of the oxidation states and times how many of them there are, like if you have multiple elements, a subscript, then you have to multiply that times the oxidation state for that one element. Then they have to add up to 0. We'll do a simple one like water. Right? This one is -2. Hydrogen is a +1. So 2 times +1 is +2, and a -2 equals 0. And that's the way it is for neutral compounds. If you have a polyatomic ion, like nitrate, like that. Rule number 3, oxygen is a -2, right? It's actually by itself. It's not hooked to itself. All these oxygens are bound to nitrogen, not to each other. So each oxygen is a -2, which means a total of -6, right? So the sum of this one plus that one has to add up to that charge. So how do you do that? A +5 and a -6 is a -1. Okay? Now, here's the way I do it. If I want to find out what that one is, I say, okay, I've got -6 over here, but I got to reserve one of those minuses for the charge. So I say, I really only need to balance -5. So that means this one has to be a +5. Okay? That makes more sense to me. All right. So how do we do oxidation? Here's some practice doing oxidation states. What's the oxidation state of each one of these elements? Okay. Potassium. Potassium is an alkali metal. It's always +1. Right? Oops. Sorry. About to give the store away. Dichromate ion together is always -2. Right? And that makes sense. If potassium is a +1 and there are 2 of them, then this whole ion has to be a 2- to balance it. So if you look at the dichromate ion, like that, then you know that it has to add up to a 2- charge. Oxygen is a 2-, so that's -14 total. But you need to reserve 2 of them. So -12 is all you have to neutralize. So you've got 2 of these that needs to be a +12. So each one of them has to be a +6. So that's why potassium +1, chromium +6, and oxygen -2. And if you add all these up times their respective numbers of atoms, then you'll find that this whole compound is neutral. How about this one ion, carbonate? Okay, oxygen is always 2 minus, so it's a -6 here. Reserve 2 of them here, -4. So this has to be a +4, and there's only one of them. So carbon is +4. Okay, we just do that all the way down. Now, when we get to PCl5, that could present a problem. Because I just told you that chlorine could be multiple oxidation states. Well, in this case, when you're presented with that problem, chlorine is a -1. Right? So if it's a -1, -5 total, this one has to be a +5. If you don't do it that way, then you can't solve the problem. Sf4 Sulfur Tetrafluoride. Fluorine, of course, is always -1. So that means sulfur has to be a +4 to balance the charges. Okay, that's practice doing oxidation states. Let's see. I left out a term. So when you have, let's see, when you have this plus this yields this, there we go. Then this is going to go from 0 to a -1, and this is going to a +1. So this is going to gain an electron. Actually, there are 2 chlorines, so it's gaining 2 electrons. And that is reduction. This one is going to, has a loss of 2 electrons. It's oxidation. Okay, so for this to be oxidized, it must be exposed to an oxidizing agent, something that draws the electron away from it. This is the oxidizing agent. Vice versa, this one is the reducing agent. Okay? So if it becomes oxidized, it is a reducing agent. And if it becomes reduced, it's an oxidizing agent. That's what this little blurb says right here. Okay. Now, can we identify which ones of these are redox reactions and then identify the oxidizing agent and the reducing agent? Okay. Well, we can make it quick, right? If all we're going to do is say which is redox. Notice there's an element there, it's in a compound over here. There's an element there, started in a compound. That's an oxidation reduction reaction. This one be a little more difficult. You would have to judge whether or not the chromium was oxidized or reduced, and you just calculate the oxidation state, and you find that this reaction right here is not an oxidation reduction reaction. But this one is. Notice the copper is in a compound here, but one of them is over here. Actually, you got 2 places. That's a special kind of reaction. It's called a disproportionation. And let's see, that one is, and that one is. So let's look at that copper. 2CuCl aqueous yields CuCl2 aqueous and copper solid. Okay, so we've got a copper here and a copper here, and we've got two of them here. So what's happening? Well, what's the oxidation state here? This is a -1, so this must be a +1. Right? What's this one? 0. What's this one? Well, this is a -1, so this one has to be a +2. So one of these coppers goes from here to here, and it gains an electron. So that means it is reduced. And one of these one of these is the oxidizing agent. Okay, the other one goes here, and it loses an electron. It is oxidized. So it's the reducing agent. In this case, copper 1 chloride is both the oxidizing agent and the reducing agent. But they're separate molecules. One of them does one job and another one does the other job. Okay, how do we balance equations for oxidation reduction reactions? Sometimes you can take a redox reaction and balance it just like you would any molecular equation. No problem. But other times, it's quicker and easier to use oxidation reduction to help you balance. And then first you balance, you write the compounds, of course, reactants, products, get those right. Then you decide what's the oxidation state on all your elements, find out which ones are reduced, which ones are oxidized, draw your tie lines for the oxidation and reduction. Then you balance the oxidized and reduced species so that you have an equal number of electrons transferred. Balance the electrons. Now, once you've got the electrons balanced and the oxidation states established, you finish balancing the equation. Because once you've got those established, then the rest of it will not change that. So let's see, we got an example here. Looks like we do. There's the unbalanced equation. Let's see, what did it say? Solid zinc, aqueous hydrochloric acid, produces zinc 2 chloride and hydrogen gas. Okay, so there's your zinc, there's your hydrochloric acid, produces your zinc chloride, aqueous, and we've split it into separate ions, right, just so that we can actually keep track of the oxidation states easier that way. And then the hydrogen gas. Right? We know it's oxidation reduction. There's an element that came from a compound. And there's an element that produced a compound. Okay? So what are the oxidation states? Well, there you go. 0, plus 1, minus 1, plus 2, minus 1. So chloride didn't change. Hydrogen did. Zinc did. So in that case, chloride is really a spectator. Right? How many electrons are transferred? Well, 2 electrons were lost to go from here to here. And 1 electron was gained to go from here to here, as it's written. Right? So we're just redrawing this in. Okay, each atom gained an electron for hydrogen. That should be shifted over a little bit. That shouldn't be on chlorine. It should be over hydrogen. Let me make a note of that. Because that looks funny. Okay. So how do you balance it? Well, if 1 electron per hydrogen is transferred and you end up with 2 over here, that means you need 2, really. So for 2 electrons to be transferred to this many hydrogens in that molecule, you actually need 2 HCl's over here. So we put the 2 here, and that makes 2 electrons gained, and we've already got 2 electrons lost right here, so the electron's balanced. Now the question is the rest of the equation balanced? Well, let's see. With a 2 in front of that HCl, we now have 2 chlorines, right? So we need to put a 2 in front of the chloride, right here. Okay? Now that should balance. Let's see. 1 zinc, 1 zinc. 2 hydrogens, 2 hydrogens. 2 chlorides, 2 chlorides. It's balanced. That was an easy redox mediated equation balancing. Oh, that's it. So work on those review problems. They'll give you plenty of practice, and then come back on Wednesday, and we'll definitely get into chapter 3 and wrap chapter 3 up. If we have time, we'll look at chapter 4, but we have an extra buffer day the following Monday that we can use to work out any kinks. And then that following Wednesday will be the second exam.